Okay, let's look at some other examples where we're using the second fundamental theorem of calculus with the chain rule. Let's say we want to find the derivative of the function little hx, and the function is given by the integral from 0 to x squared and t squared over t plus 1 dt. Now, the difference between this function and the previous functions are right now the upper bound is not x. The upper bound here is a function containing x. Here, in this example, the function is x squared. So we are not able to use the result directly. Okay, we are not able to use the result directly. So if you put the answer like if you think the answer is if you think the derivative is with plugging x squared into the function like this. Now this will be incorrect. Now this is not the answer. Okay. So to think about how to solve this problem, let's say if we have a function fx and if fx is given by the integral from 0 to x and t squared over t plus 1 dt. Okay, if the function is defined in this way, then we can find the derivative of fx using the result directly. So the derivative will be x squared over x plus 1, right? Now, the difference between the function hx and the fx is the upper bound. Since the upper bound is x squared, so we can express the function little hx into f of x squared. Why? Because for this function fx, the input is x, right? The input is x, which is here. So when we change this input into x squared, that will give us the function hx. So that's why hx equals f of x squared. Okay, once we get this relationship, then we can know that the derivative of hx will be equal to the derivative of f of x squared, right? So if I can know what is the derivative of f of x squared, I will be able to know what is the derivative of hx. Okay, so to find the derivative of this function, now this function f of x squared is a composite function. And when we are talking about the derivative of a composite function, we're going to use chain rule, right? So let's see what is the inner function and outer function of this composite function. The inner function is x squared, right? And the outer function is this f of x. And we already know, and according to the chain rule, the derivative of this function gonna be equal to the derivative of the out function with the inner function plug in, and times the derivative of the inner function. Okay. Now, since we know what is the derivative of the out function, we know what's the derivative of the out function, which is this, which equals this. then the first term we can write as so the first term is x squared raised to the power of 2 over x squared plus 1, right? Because here we're gonna plug in x squared into this result, so we change every x into x squared, and then multiply by the derivative of the input function, which is 2x. So the result is x to the fourth over x squared plus 1 times 2x, which equals 2x to the fifth over x squared plus 1. So the derivative of function hx is this. Okay, so this is the formula for doing this when the upper bound is not x, when the upper bound is a function containing x. When we take the derivative of this integral, the result equals the function little f with this function gx plug in, and then multiply by the derivative of this function. Okay. See, just like what we did here, right? Okay, let's take a look at another example. Again, here the upper bound is a function for x. Right now, the function is x to the third. So using this result, the derivative of function little fx equals cosine of x to the third, right? F of gx, and then multiply by the derivative of x to the third. The derivative of x to the third is 3x squared. Now, be careful. We are not able to combine x to the third with 3x squared, right? Because x to the third, this term is the input of the function cosine. So the result we either write as a 3x squared times cosine of x to the third, or we write as a cosine x to the third times 3x squared. That's it. Okay. Okay. Now, what if the lower bound and the upper bound, they are both a function containing x? In that case, we're gonna split this integral into two integrals. Like here, we split this into integral from hx to a constant ft dt, and plus another integral from the same constant to gx ft dt. And then for the first integral, we switch the lower bound with the upper bound. So we write this as a negative the integral from a to hx, and then once we get here, we can use the result from this to find the derivative. Okay. Because once we get here, when we are taking the derivative of the difference of these two integrals, we can do this by finding the derivative of the first integral okay, and minus we find the derivative of the second integral. And the derivative of the first integral is f of gx times the derivative of gx, and minus the derivative of the second integral is f of hx times the derivative of hx. Okay, let's use this method to try this problem. So first, so the function, the gx is x squared, and the hx is x, and f of t is the square root of 1 minus t squared. So we can first split this into two integrals. So one is from x to some number a, and the second integral is from this number a to x squared. And then for this integral, for the first integral, I switch the bonds. Okay, now when I find the derivative of function theta fx is equal to the derivative of this integral plus the derivative of the second integral. Okay. To find the derivative of the first integral, we can use the result from the second fundamental theorem of calculus directly, because the upper bound is x, so the derivative is negative square root of 1, we substitute x for t minus x squared. To find the derivative of the second integral, now the upper bound is a function of x, so we are using a chain rule. So first we substitute x squared for t. So instead of having t squared, we have we're gonna have x squared squared. So that's x to the fourth, and then multiply by the derivative of x squared, so 2x. And if we simplify our answer, it's gonna be like this. Okay. Okay, it's gonna be like this.